Okay, so let us continue with some more problems on thermodynamic relations, and more of that you practice, you will be better off actually doing that, and you will see that different times you need different type of tricks. Sometimes you will need Maxwell's relations, sometimes you have to use Jacobian technique, sometimes you have to go just the definition of these thermodynamic potentials like du, dA, dG and dH. So, once you have these ammunitions with you, then you should be better off converting one form to the another form and then getting the desired answer that you want. So, today we are going to practice some thermodynamic relation problems, a few of them. So, that we will see that what kind of tricks we need along the way. So, I myself do not know about the problems right now. I have not done that before. So, we may get stuck at some point, then we will see how to solve them and things like that. Okay. So, let us continue with that. So, first problem that we have to do is we have to show that del u by del V t equal to minus T del V del T p minus P del V del P t. This is almost similar to the Joule's expansion problem, right. So, we can always start u as, or we can start u as a function of v and t, and we can expand u in terms of v and t. So, du equal to del u by del v t dv plus del u by del t v dt. Now, will that help us? No, because we only need this particular quantity del u by del v t. So, that will not help us, because we want only this thing. So, let us use our knowledge about du. So, du as you know is T ds minus P dv, this we know, right. And once we know that, and we have to get du by dv at a constant t. So, we can differentiate both sides with dv. So, we get du. So, this u is small and there is this u is capital. So, we will just use capital thing. So, del u by del v t. So, what we did is we took the differentiation with respect to v at a constant t, whatever is asked for. So, as I told you that right hand side t will not be differentiated, because only the differential will be will be affected. So, del s by del v t minus p del v by del v t. So, which means t del s by del v t minus p, because del v by del v is 1. Okay. So, what they have asked for is del v by del t p minus del v by del p t. So, we do not see yet anything that is close to that. So, we will have to expand a little bit more and see what we can get out of that. So, we know that from Maxwell's relation that S p T v del s by del v is del p by del t at a constant v, and that is also not there. What we have here is an expression of p, but we can actually we can do a little bit of trick here, and we know that when you write S p T v, then del v by del t at a constant p is nothing but del s by del p at a constant t minus of that. So, somehow we need del s by del p, and then del v by del p of course will not come, but you see we need derivative with respect to p, not with respect to v. We need with respect to p in order to get that. So, I think the question may be wrong, we will just check. So, let us start with u again. Du is TdS minus PdV, and let us take derivative with respect to P. I think the question is wrong. So, du by dP at a constant T is T del S by del P at a constant T minus P del V by del P at a constant T. Okay. Now, if I do SPTV, then we know del S by del P at a constant T is del V by del T at a constant P, negative of that. So, minus T del V by del T at a constant P minus P del V by del P at a constant T, and what is asked for? Minus T del V by del T at a constant P minus P del V by del P at a constant T. Okay. So, that is what we get. So, our question was wrong, it should have been del V by del P at a constant T, sorry, del U by del P at a constant T and not V. Okay. So, let us go to the next problem. Second problem, show that C V equal to minus T del 2 A by del T 2 V. Okay. So, what is the definition of C V? We know that C V is del U by del T at a constant V, that is the definition of C V, right. So, how can we actually connect to something like a second derivative of A? So, we have to understand in that is that when we write C V as del, so that means we have to get first del A by del T, then only we can get the second derivative with respect to V, right. So, del A by del T. So, what is A? So, we have to know that what is A. So, as you know, A is U minus T S. So, d A is d U minus T d S minus S d T. So, we can even break it up and say that d U T d S minus P d V. So, it is minus P d V minus S d T. So, that is our A. Now, if we take a derivative with respect to T at a constant V, at a constant V, this term will be 0 and that will be minus S. So, del A by del T is minus S. Okay. So, then we know how to solve the problem. So, this is the definition of C V, and we know that this definition also can be written as del S by del T, T del S by del T at a constant V. Okay, that solves our problem, because we know that S equal to minus del A by del T V, that is our S, and this derivative we have to do with respect to V again, which means that C V now becomes minus T del 2 A by del T 2 at a constant V, and that is proved. Now, we will go to the third problem. Del H by del P at a constant T is equal to V minus T del V by del T at a constant P. So, this is what we have to show now. Okay. Here also we can write first formula of H. You know H equal to U plus P V. If you just start from the beginning, then d H is d U plus P d V plus V d P, and you know d U is T d S minus P d V plus P d V plus V d P. So, d H is nothing but T d S plus V d P. So, you see we are just using the definition and nothing else. Now, we can always take a derivative with respect to P at a constant T. So, del H by del P at a constant T is T del S by del P at a constant T plus V. And now, this is very simple. So, we are going to use Maxwell's relation SPTV. So, del S by del P at a constant T is del V by minus del V by del T at a constant P, okay, plus V, and that is del V by del T, that proves it. Let us start the fourth problem. says that del H by del V at a constant t is equal to V square del P del T V minus del T by V by del V constant P. Okay. So, you see the right hand side is a little bit complicated. So, let us first get the right hand side right. So, what is del T by V by del V? What is this one first? Let us see. So, that is del V of T by V at a constant P, which is product of two functions. So, it is T del V by 1 by V, which is minus 1 by V square plus 1 by V into del T del V at a constant P, which is minus T by V square plus 1 by V del T by del V at a constant P. So, let us keep that as equation 1. So, because that is what we have to bring. So, we have to show then del H by del V at a constant T is equal to V square del P del T V and minus this quantity. So, minus 1 by V del T del V P plus T by V square. So, this is what we need to show. As you can see, there are 3 terms here, that is okay. So, let us see how you can do that. We can start with the definition of dH, which is TdS plus VdP. Let us take a derivative with respect to V at a constant t. So, del H by del V at a constant t is what we want, that is T del S by del V at a constant t plus V del P by del V at a constant t. Now, we know from Maxwell's relation, we just quickly write SPTV. We know that del S by del V at a constant t is nothing but del P by del T at a constant V. So, you see we got del P by del T, but we got a T and not a V, we need V square. So, that also is not there, and del T del V is also not coming from this. So, what we are going to do is that we are going to now break down this del T del V and see what we get from there, or alternatively we can break down this one, whichever is fine with us. We can do this one, del P del V T. So, del P del V T is nothing but del P T by del V T. We need del T del V, which is we need T P by V P. T P is already there, V P. So, I write P V. So, then we write P V and V T. Okay. So, now we can exchange this both numerator and denominator positions, and we can get the same thing, 2 negatives. So, this is fine. And now, in this case here we just change only one, let us keep it as P V and let us change as T V. So, then we get d P dt V again back from there. So, you see this one is nothing but del T by del V at a constant P, which we actually wanted here. But in addition what we get is minus del P del T at a constant V. So, this is nothing but a product. So, therefore, del H by del V at a constant T equal to, actually from equation 1 we can say T del P by del T V plus V del P by del V T which is from equation 2 will be into minus del p by del t v del t by del v p. Now, I can take del p by del t v common, going to get t minus v into del t by del v p. Remember, I need to be here. So, let us see, we need, in order to get this particular thing t by b by v, we need to be here. So, okay. So, we can that was equation 1 already. So, I can just make it as equation number 2, this one, and as 3. So, this from 2 we get, and 3 will from 3 we get this one, this particular thing from 3. So, now t minus del t by del v, let us see here, t minus, if I take a minus of that, if I multiply by v square, then it will be then it will be t minus v into, yes. So, from equation 1 now, so I will just write equation 1 once more. What we got is del t by v, I need to see it once more by del v at a constant p, at a constant p is equal to minus t by v square plus 1 by v del t by del v at a constant p. Just check once more. Yep. So, that was from equation 1. Now, multiply by v square both sides. So, we get v square into del t by v by del v at a constant b is minus t plus v into del t by del v at a constant p. Take the minus on this side. So, minus v square del t by v by del v p is t minus v del t by del v at a constant p, and that is what here, that is here. So, we can say that del h by del v at a constant t is equal to del p by del t v into minus v square del t by v by del v p. However, that was not the one to be proven. I think it is a multiplication rather than a minus sign. So, if we found another mistake, but we know that it is just a mistake in the way it is written. If we wrote this in the beginning, this part here, then there is absolutely no problem, otherwise it looks like a minus sign. Okay. So, basically, yeah, so that is the same problem that is appearing here also. So, there is should be a bracket. So, it is minus v square del p del t v and del t by v by del v p. So, if you can do that, you can even find out the mistakes from the derivation, that is even better, right. We go to the next problem, where we write, or it is a v, problem v, write C v as minus t del p del t v del v del t s. Just to make things complicated, C v is very simple, del v by del t at a constant v. why one should write in such a complicated form. However, this is just an exercise, so that if you can do that, you can do many other problems when you need. So, let us try to do that. So, start with the definition of CV, del u by del t at a constant v, and that is what CV is. Now, you see we can always write u as product of expand in terms of v and t, or yeah, we can expand that in terms of v and t, or u is a natural function of s and v, right. So, do that in terms of s and v. So, del u by del s, and it will give you the same thing, by the way, del u by del s at a constant v ds plus del u by del v at a constant s dv. So, we did that constant s because see this constant s is coming. So, as you know, it is nothing but T ds minus P dv. You see the P then again is constant of like P is like del u by del v at a constant s, that is the P. So, I can always take derivative with respect to t, it will give me del v del t, but it will not give me the s. So, SPTV if I do, let us see, then del v del t at a constant p I get. I of course get del s del t del v at a constant s, which is just the inverse of this. You can use that. That way we will get that. If that is the case, del t del v at a constant s is nothing but del p del s minus del p del s as a constant v. If we only need with respect to s, then what else we can think of is we can expand u in terms of v and t and see what we get from there. We can do many different ways, but we are just thinking what would be the best choice. Otherwise, we will use Jacobian anyway and do that. We can do the Jacobian and we can bring the s in the numerator anyway. So, that is not a problem. I am just showing you that this s can appear in this particular form. So, if you take a derivative with respect to like v, then you can have the s. For example, del u by del t, I can have del u by del t v, then del v by del t s. Yeah, that is possible. That is possible. So, okay. If I let us say try del u by del s at a constant v is just nothing but t. Okay. Now, this means I can write del u by del t, del u by del t at a constant v, then del s by del t by del s at a constant v. Okay. So, can I write that? Let us see, use Jacobian and show you. So, this quantity del u by del s at a constant v is nothing but del u v by del s v. So, I wrote del u v by del t v and then del t v and then del s v. Now, that becomes del u by del t at a constant v, and this becomes del t by del s at a constant v. So, I can write that. That is also nothing but t. Del u by del t at a constant v is by definition C v. Okay. So, and this is nothing but inverse of del s by del t at a constant v inverse is t. So, C v is del s by del t v t. Okay. So, we got t del s by del t v, and that is not a big deal. because we already know the formula, right. But see, then we have to prove. So, since we got T already, we have to prove that del S by del T is nothing but this thing. So, we have to prove del S by del T V is nothing but del P del T V, then del V del T S, and actually minus sign of that. That is what you have to prove, and that is easy by Jacobian. For example, we can write del S by del T V is del S V by del T V is, now we want P T V, right. So, we can have del P V by del T V, then del S V is still there, and we have to write P V here, because then P V cancels and S V and T V will remain, and that is del P by del T V, and this is del S by del P V. Now, we are going to use Maxwell's relation S P T V, and we know del S by del P del, okay, here it is. So, now we are going to use, okay. So, one more step, del P by del T V, then it is del P by del S at a constant V, but inverse of that. Now, we know that del P del S V is del T del V S, minus of that. So, that is minus of del T del V at a constant S, wait. So, inverse of that, which is minus del P del T V is del V del T at a constant S, and that proves it. So, now let us go to the sixth problem. Del V del T S, we have to show that it is minus C V. I think kappa denotes kappa T according to the notation, and beta is nothing but alpha. So, we have to show this. Now, once you see that we have to derive or break the thermodynamic relations into the heat capacities finally, like alpha, kappa T, C V and all that, then we know that we have to use Jacobian. We have to break down all possible ways. So, we will just straight away do that, because that becomes extremely straightforward using Jacobian. So, we write del V del T at a constant S as del V S del T S. Okay. And of course, we can use a trick and do that, or we should do that anyway, because we need C V, and C V means del S by del T, we need that, and we need kappa T. So, we need a P T term. So, we will add a P T term. So, V S and T is definitely required, V is also definitely required. So, we will use a V T term here, we will see. Okay. Then we get straight away the C V right away, and then we get V T and T S. We will see how helpful that is. Now, so this means that we can write as S V T V, and this side we can write using a minus sign as del V T and del T S. Okay, we do not write the minus sign right now. So, we get here del S by del T at a constant V, which is C V by T, we know that, and that is del V T by del T S. We did not do anything with that yet. Was it helpful? I do not think it is so helpful. okay, of course, we get Cv by T here. We need, okay, I think it is helpful. We know why it is helpful, because we have already done that before. That is why. So, for example, we know that kappa T is by definition, kappa T is isothermal compressibility. So, it will be minus 1 by V, we have to compress, right. So, del V by del P at a constant temperature, and alpha we know as coefficient of thermal expansion, which is del V by del T at a constant pressure. So, now kappa T by alpha, we have shown that before, but I will show it here again. Kappa T by alpha is minus 1 by V del V by del P at a constant temperature by 1 by V del V by del T at a constant pressure. V and V cancels, giving is minus del V by del P at a constant T, and we can always write the inverse way, del T by del V at a constant P. So, kappa T by alpha is then minus del V T by del P T, from the left hand side this one, right hand side will be del T P by del V P. We can simplify it further. So, this is minus V T, and we can take a minus sign and write as T P into T P by V P. So, T P cancels, minus minus cancels, giving me del V T by del V P. We can switch both the variables and write del T V by del P V, giving me del T by del P at a constant volume. Now, that is, so now you see here, that is fine. So, now when you come back here, what we see is that we have, so now coming back to our original one, del V by del T at a constant rate. So, let us write that equation as equation 1, and or let us call that equation 1 and that as equation 2, and then write the original one, del V by del T at a constant S equal to del S by del T from equation number 1, del S by del T at a constant V and del V T by del T S. Okay, which is nothing but C V by T, we know that, and this one we can write as del T V minus of that of course by del T S or opposite. So, let us do just the opposite of that. Do not switch the numerator, switch the denominator, and what does that give us? Minus C V by T del V by del S at a constant T. That is what we get, which means we can write that as minus C V by T del S by del V at a constant T and inverse of that. Now, we are going to use Maxwell's relation, because whenever this SPTV comes, we should use Maxwell relation. So, del S by del V at a constant T is same as del P by del T at a constant V, inverse of that. And what do we learn from equation number 2? That kappa T by alpha is Okay, equation number 2 can be written one more step as del p by del t V inverse. So, del p by del t V inverse is kappa t by alpha. So, this is nothing but kappa t by alpha. So, that is also proved.